All right. So, lesson 2.6 is going to be about rational functions in the graph, and we'll get into what those are in just a little bit. But before we do that, the kickoff here, we're going to list all the possible rational zeros of this function right here. So, we're looking first at the constant function here. So, I'm going to put a C. So, factors of the constant term 4 here would be plus or minus 1, plus or minus 2, plus or minus 4. Next, we're looking right here at the leading coefficient, so I'm going to put an L. Factors of negative 1 are just plus or minus 1. So when we do this, we're doing that constant factor over the leading factor. So they're all going to be over 1, so all these here are going to be plus or minus 1, plus or minus the 2, and plus or minus the 4. And that's how we're going to leave it. Now, rational functions are going to be functions where we have a polynomial over a polynomial. So they're in a fraction form. So variables on top, variables on the bottom. Now, the main thing here is we can't let the bottom be 0. Because anything equal to 0 on the bottom, we can't divide it by 0, that's bad. So keep that in mind. But with doing that, we're going to have to find domains of this because we may have to restrict it a little bit. Like here, for the domain here, the top doesn't matter because the top can be whatever and the fraction's still fine, but we can't have the bottom be 0. So that's what we're going to do. We're going to set the bottom equal to 0 and we'd solve it out. So this here would factor out to be x plus 3, x minus 3. So in other words, x is going to equal negative 3 and 3. So that's what's going to cause the bottom to be 0. So our domain is going to be everything except those. So it would be all reals except x cannot equal negative 3 and 3. So we kind of did this a little bit before in the pre-chapter, but keep in mind, we're building into stuff here, so we're just going to hit it again, make sure you're good. But that's how we found our domain. It's really going to be everything except what will make the bottom be 0. Okay. Now, your basic rational function is the reciprocal function here of 1 over x. So how it's going to look like this. So the graph is going to be coming along. We're going to kind of dip down, then all of a sudden we're going to shoot down. From the other side, we're come flying down, and then we level off and stay above 0 here. So as we approach 0 on each side, so it's going to go to negative infinity on the left. So the closer we get to 0, we're going to go down to negative infinity on the left side. As we get close to 0 from the right, we're going to go up. Now, as we go out towards the left, we're going to go towards 0. And as we go to the right, we're going to go towards 0. So what we're going to have here is some asymptotes, and we're going to get into that in a little bit here. But one way we can write this is with using arrow notation. Now, arrow notation is meaning just as we approach. So x arrow a plus means x as we approaches our a, whatever a is representing from the right. So if it's a plus up here, it means from the right. There it means from the left. But the arrow just means we approach. So as we get closer to that value. So x as we approach a from the left. X as we approach infinity. X as we approach negative infinity. So as x changes to this value, what's our graph doing? Now, if it's infinity or negative infinity, there's only one way to go to that. Negative infinity, we're heading to the left. Positive infinity, we're heading to the right. But if it's any other value, we could approach it from the left or the right. So maybe from one side it's doing one thing, from the other side it's doing another thing. Just like what we're doing here. From the one way, it goes down. The other way, it's going up. Okay? So if we use arrow function here to describe that reciprocal graph. So the graph is doing this. So how we would do this is, so these worded paragraphs, we're going to write using arrows now. So we would say x approaches negative infinity. So as we go left, y approaches 0. So that's what our graph is doing. X approaches, now we're going to go to 0 from the left side, our y goes to negative infinity. So as we're coming from the left side, our graph is going down, so that's what y is doing. X approaches 0 from the right side. So now as we come this way, we're shooting up, so y would approach infinity. And lastly, x, as it approaches infinity, our y is approaching 0 again. So as we go out, we get closer and closer to 0. Right? So using arrows, arrows just mean it approaches. If it's got the negative on the back side, so on the right side of it, that means we're going from the left. If it's got a plus, then we're going from the right. So another basic function that's a rational function is the 1 over x squared. So here, as we come into 0, they're both going to go to infinity. So x equal a is going to be that vertical asymptote. So right here, our x equals 0, because we're going to approach 0 but never actually cross, and that's what an asymptote is. It's a line, vertical line, if it's a vertical asymptote, but it's an imaginary line that you don't see, but our graph gets close to it but never actually crosses it. So in this case, we'd have x equals 0 would be that vertical asymptote. Now, to find these vertical asymptotes, you're going to factor it, and then we're going to get rid of any common factors. If it cancels out, it's not going to be an asymptote. That's actually going to be a hole, but that's for something at another time. But if it doesn't cancel out, whatever will make that be 0, that'll be your vertical asymptote. So I'm going to rewrite this x plus 3 over x squared plus 9 over here. Now, so the first one here, if we factor this out, this is going to go to x minus 3x plus 3. Now, on top is just an x, so there's nothing that we can cancel out there. So in this case, we're going to have a vertical asymptote at both negative 3 and 3. So if we set each of these equal to 0 and solve, we'd add the 3 over, we'd subtract the 3 over, and get our negative 3 and 3. Okay. This one here, again, factors out to x minus 3, x plus 3. So we have an x plus 3 at top, so that factors can reduce. And so what we have here is 1 over x minus 3. So the only thing that vertical asymptote could be is when, if we'd set this equal to 0, we'd add the 3 over. So x would equal positive 3 is where the vertical asymptote. Now, we would have a hole at x equals negative 3. So what that means is, because it cancels out, the graph would do something like this, where it's going along, all of a sudden, hey, there's a spot where it doesn't exist, and then it continues. Whereas the vertical asymptote, we're going to be approaching it and either curving up, curving down, something. Okay? Last one here. We can't factor this. This is x squared plus 9. It's not a difference of squares with a minus. So in this case, no matter what we do, we're always going to get something other than 0. So here, vertical asymptotes, none. So it's only if something causes the bottom to be 0 and it can't be reduced with a factor on top. So just to go into a little more detail, so just because that value in the denominator of a rational function is a 0, doesn't mean it's a vertical asymptote. So again, if the factor of the denominator can be reduced with a common factor in the numerator, so 1 on the bottom can be reduced with something on top, then it's going to be a whole, not a vertical asymptote. So like I said, that x plus 3 reduces with the common factor on top, but even though it doesn't make a vertical asymptote, it still doesn't exist. It still causes a problem, but it's a whole and not an asymptote. So it's going to come, skip over it, keep going, where the asymptote, as it approaches it, it can't cross it. So it's either going to curve up to infinity without bound, or it's going to curve down to negative infinity without bound if it's a vertical asymptote. And that's where it doesn't cross out. If it does, it's just going to be a hole, so think it's just a blip. It's like a speed bump. You're going to hit it, boop, keep going. Okay. Now, as you noticed on those other ones, we also have horizontal asymptotes. So this is going to be a horizontal line where we're going to approach it and we're going to level off. Now, one difference with a horizontal versus a vertical. A vertical you never cross. Horizontal, it may cross it, but then it comes back and levels out and gets close to it. So that's kind of what I just said there. So this is kind of a lot going on with vertical asymptotes, but this is essentially what it comes down to. So what we're going to do is we're going to look at the biggest term on either side. So that leading term on the top and the bottom. Now, if the top is smaller, so like for example, if the top is say x squared and the bottom is x to the third, your horizontal asymptote will automatically be y equals 0. If they're the same, so let's say it is 4x squared over 3x squared. Your horizontal asymptote is going to be the coefficients of that function. So it's going to be 4 over 3. So it's just going to be the coefficients in front. Now, if the bottom is smaller, so if it was, say, x to the third over x squared, for example, then no vertical asymptote. So top is smaller, it's y equals 0. If they're the same, it's whatever those coefficients are, that's what it's going to be. So this would be y equals 4/3. Now, if the top is bigger, then no vertical asymptote. And that's going to be something different. We're going to get into it in a little bit. But before we do that, so find the horizontal asymptotes of each of these graphs. Well, the first one here, we're looking at these biggest terms. So we're looking at those. Top is an x, bottom is x squared. So the top is smaller than the bottom. So horizontal asymptote, y equals 0. Next one. Again, look in here. Leading coefficients are leading terms. Here they're both x squared. So horizontal asymptote, I don't know why I keep putting A's, is going to end up being y equals, now, 4 over 2, which 4 divided by 2 is just 2, so y equals 2 would be your horizontal asymptote. Again, look in here. Top is bigger than the bottom, so horizontal asymptote, none. Not going to happen. So, top smaller, y equals 0. If they're the same, it's the coefficients, the numbers in front. Also, simplify those. And then if the top is bigger than the bottom, there's not going to be a horizontal asymptote. So these are the only places where it happens. Now, more so, this has to be bigger, but generally it's 1 bigger than the bottom will lead to this. If it's bigger than that, then it might not always happen. But at least for here, we're good. Now, graphs of rational functions can be transformed just the same as quadratics. So we can shift them, stretch them, all that stuff. Now, when it comes to graphing them, you're going to look at these 7 things. So these are kind of going to be your guidelines on what to do working through this, all right? So, first off, we're going to determine if the graph has any symmetry. So that's what we're looking at, is it even or odd? If it's even, it's going to be symmetric about the y-axis. So that's where all the exponents are squared, or to the 4th, they're an even number, or there's a constant. If it's odd, where all the exponents are odd, then it's going to be origin symmetry. So we'd take it, we'd be able to rotate it about the origin and match up. So, looking at those, then we're going to find the y-intercept by putting 0 in for x. We're going to find the x-intercept by setting our top equal to 0 and solving it out. We're going to find any horizontal asymptotes our vertical asymptotes by solving the bottom set equal to 0. Find those horizontal asymptotes by following the rules there. Then we're going to plot at least one point between and beyond each x-intercept in the vertical asymptotes, and then we graph it. So this is how this is going to work. So starting off, symmetry. If I put a negative in, this would change. This would change. This one would stay the same. So no symmetry. Okay. Number 2. If I put 0 in here, 0 over 0 minus 1 would be 0 over negative 1, which is just 0. So y equals 0. 3. I'm going to set 2x equal to 0. So I divide by 2. X equals 0. So that's going to be my x-intercepts. So I should have y, the or the colon. So it should be there. So 4, find a vertical asymptotes by solving the bottom equal to 0. So x minus 1 equals 0. I'd add the 1 over. So x equal 1 is going to be where the vertical asymptote. Yep, sorry about that. So x equals 1. So horizontal. Again, looking at this first one, they're both the same. So 2 over 1, which is 2. So horizontal, y equals 2. So making good progress. On to 6. 6, plot at least one point between and beyond each x-intercept in the vertical asymptote. So this is where it's going to come really handy if you have a graphing calculator. So in my graphing calculator, I'm going to put that equation in. So the top, I'm going to put in parentheses 2x. Now we might not need it here since it's a single term, but definitely on the bottom we do with x minus 1. So have that equation in, and I'm going to go to my table, second table. And if there's stuff here, just delete it all out. Now, we're going to have a point in between and beyond each x-intercept and vertical asymptote. So x-intercept is going to be at 0. Vertical asymptote is going to be at 1. So I need something on either side and in between. I'm going to go negative 1, 0.5, and 2. So that's what I'm going to put in here. So negative 1, 0, 0.5, 1, and 2. So you're going to put all of those in there. Now, on your vertical asymptote, it should be an error. So you shouldn't get anything there. So if I draw these down, this is going to give us a y value pretty much here. So negative 1, we get 1. 0, we get 0. 0.5 is negative 2. This again is that vertical asymptote, so there shouldn't be anything there. And then 2, we get 4. So when we go to graph this for number 7 here, so I'm going to plot these points. So at negative 1, I'm at 1. 0, I'm at 0. At 0.5, I'm at negative 2. At 1 here, we have a vertical asymptote. And at 2, we're going to be at 4. So how this graph is looking is this. It's coming along, curving down. Now keep in mind we had a horizontal asymptote here at 2. And so this other one, if I extend it up, we're going to do the same thing. We're going to come down and go that way. So the graph, and I'm going to check it here, should look like that. And it does. Okay. So, do another one. So we're going to graph this one here. F of x equals 2x to the third, x squared minus 4. So again, we check for symmetry first off. Top is odd, bottom is even. They're not the same. So this is none. So second thing we're going to do is, I should have kept my paper. Here we go. Second thing is find the y-intercept. So if I put 0 in here, again, single term on top, 0 to the third is still 0. 0 times 2 is still 0. Doesn't really matter what's on the bottom because 0 over anything is 0. So that's going to be our y-intercept. X-intercept. So 2x to the third. We're going to set that equal to 0. We set our top equals 0 and solve to get our x-intercept. So we would divide by 2 of x to the third equals 0. So cubic root x would end up being 0. So we still only have 1. But that happens 3 times. It's going to have a multiplicity of 3. 4, we're going to find our vertical asymptote. So x squared minus 4 equals 0. This will go to x plus 2, x minus 2. So in other words, x would equal negative 2 and 2. Horizontal asymptote. Again, top is bigger here. Not going to be the same. So looking at these first terms, again, is where I was going with that. So when the top is bigger, there is no horizontal asymptote. So the top has to be smaller for it to be y equals 0. If it's the same as coefficients in front, here the top is bigger. So no horizontal asymptote. So for number 6, we're going to plot one point between and beyond each x-intercept of vertical asymptote. So vertical asymptote is going to be at negative 2 and at 2, and our x-intercept's at 0, so 1 in between and beyond. Negative 3, negative 1, 1, and 3. So a few more points to plot here. Again, I'm going to take my graphic calculator, I'm going to put that equation in, so I'm going to clear out the one I got. So in parentheses, 2x to the third and we're going to divide that by, and again, make sure you put this in parentheses, x squared minus 4, close your parentheses. So it should look something like this. So our 2x squared to the third in parentheses on top divided by x squared minus 4 on the bottom. So again, when I go to my table, second table, there's stuff here, so I'm going to delete that all out, and I'm going to put in these values. So negative 3, enter. Negative 2, enter. Negative 1, enter. 0, enter. 1, enter. 2, enter. 3, enter. So we'd have all those up there. So again, those are our y values. These here are the x values. So negative 3 would give us 10.8 negative. This is that vertical asymptote, so you should get an error. Negative 1 is going to be 1/3. 0 is 0 again. 1 is a negative 2/3. Sorry, negative 1 should have been 2/3. Oh, sorry about that. So, 0.667's what we get, which is 2/3. That was my bad. 2 again, vertical asymptote. 3 is going to be at 10.8. So, if we go to graph this, we don't have a horizontal, so we have to worry about that. But vertical at negative 2 and at 2. Y-intercept, x-intercept, both at 0, 0. So it's going to be right there. Now, at negative 3, we're at negative 10.8. At 1, we're at 2/3. So negative 1, 2/3. 0, 0. 1, we're at negative 2/3. And at 10, or at 3, we're up here again at 10.8. So, what that means is this. This one's going to be curving. Actually, I don't remember what this one's going to curve. But here we're going to be doing one of these. Now, here we're above, here we're below. I'm going to go to the graph here, which all it gives me is this right now because of my window. So I'm going to change my window to negative 20, 20 for my X and my Y's. Okay. I was wondering if that's what I was doing. But yes, this is what we're going to have happen here. Now, if I go to graph this is coming like this. This one's coming like this. So, if we go back to this graph, kind of looks like we're slanting through here. That's because when the top is bigger, we're actually going to get a slant asymptote. So the graph of a rational function will have a slant asymptote if the degree of the numerator is more than the degree of the denominator. So when the top is bigger, to find that, we're going to do long division. We're going to divide the top by the bottom, and the quotient, not including the remainder, is going to be the equation of the slant asymptote. Okay. Now, generally this is going to be when it's one bigger, because otherwise you're not going to have a straight line. So we're going to focus on slant asymptote here. So again, we look here, top is bigger. So we do x squared plus 0x plus 1 divided by x minus 1. Now, and I'll show that with the next one, it works with synthetic division as well, as long as this is x minus 1 or x plus 1 sort of a thing, and that x minus c form. So to get x squared, I would take it times x times x squared. X times the minus 1 would be a negative x. I subtract, so it switches signs. Those cancel. So we're going to have now x plus 1 here. So to get my x, I would take it times 1. 1 times x is x. 1 times negative 1 is a minus 1. So subtract here, which makes that a plus. We end up with 2. So this doesn't really matter. What does matter is this up here. So y equals x plus 1 is the equation for the slant asymptote. Okay. Now, this one we'll do synthetic division with. Same idea. So x minus 3, 3 goes in the box. So x squared would be 1. X is minus 4. 5 is minus 5. So bring the 1 down. 1 times 3 is 3. 3 minus, or negative 4 plus 3 is the negative 1. Negative 1, 3 is negative 3, which is negative 8. But again, that doesn't matter. What matters here is x minus 1. So y equals that is the slant asymptote. That's how you find those. Okay. So when the top has a bigger exponent, divide out the top by the bottom. What you get, not including the remainder. The remainder we don't count towards this. It's just the quotient part is your slant asymptote. So it'd be y equals that. Now, also going to deal a little bit in this chapter with some word problems here where we're dealing with the cost function. A company is planning to manufacture wheelchairs that are light, fast, and beautiful. Now, I just want to point out I did not write this up, but I would totally want a light, fast, and beautiful wheelchair. The fixed monthly cost will be $500,000. It will cost $400 to produce each radically innovative chair. So that fixed monthly cost could be electricity, paying your workers, the materials you're bringing in, all that. Maybe not necessarily materials, but it's just your standard cost to make it no matter what. Your jigs, your machines, all that. And then $400 to produce each radically innovative chair, so that's probably labor and materials. So we're going to write the cost function C of producing X wheelchairs. Well, cost function C of X is going to be equal to your 400X plus 500,000. So cost per chair plus your total cost. So this is A. B. Write an average cost function of producing X wheelchairs. So average cost So the cost per chair, which they put with the line, which is where the rational functions come in with this, would be what we have here. So the cost of production divided by how many chairs we sell. So divided by X. So C, find and interpret C of 1,000, C of 10,000, C of 100,000. So C prime of 1,000, C of 10,000, and C of 100,000. Now, we could put these in. I'm going to go into my Y equals here again. And I'm going to clear this one out. I'm going to put my average cost function in. So whole top needs to be in parentheses. So 400x plus 500,000, and close your parentheses, and then divide by X for the bottom. So then we can go to our table. Again, delete out anything that's there. And so we're going to put in 1,000. We're going to put in 10,000. And then 100,000. And so this is what we get. So per chair, the 1,000 chairs is going to be $900. The 10,000 chairs made is going to be $450. And 405 is going to be if we make 100,000 chairs. So what does that mean? Well, basically what's going to go on with D here. So what is the horizontal asymptote of the graph of the average cost function C, and describe what it represents to the company? So again, we look at our biggest terms here. They're both X. So the horizontal asymptote is going to be what the coefficients are. So horizontal asymptote is going to be Y equals 400. Now, what does that represent for the company? Well, that's your lowest cost. So no matter what, that you're always going to cost at least that, if not more. However, the more we produce, the closer we get to 400. So I'm going to put that in here. More produced, closer to horizontal asymptote. So 400 is that horizontal asymptote. The more we produce, the closer we're going to get to it. We're never actually going to get there. But that would be the lowest cost, that $400. It's going to cost us at least that per chair. However, we're going to break this 500,000 up per chair, so that's adding to it and making it more expensive. But the more we make, the more that spreads out, so the lower the cost is added on. So this would be a point we're going to do another one really similar to this one. Now, if you wanted to pause the video here and do this one on your own and then check it by watching it, please go ahead and do so. But I'm going to work it out because I'm not going to pause for you. You can pause it if you need. So, new companies hoping to replace traditional computers and the two-dimensional monitors with its virtual reality system. Keep in mind, this is an older book. This was written years ago. This was something cool and innovative they thought would happen. However, the fixed monthly cost will be $600,000 and it will cost $500 to produce each system. So we'll write that cost function. So that's A. So C of X would be equal to, it's 500 X for how much it costs for each system, plus our 600,000 fixed cost. Average cost function. It's going to be the same thing. Only difference is by finding the average cost, we divide by our X, however many we produced. C, we're going to find and interpret what each of those mean. So C of 1,000, C average of 10,000, C average of 100,000. Same thing. I'm going to put this in my y equals, so I'm going to have to change this one up. Should have parentheses 500x plus 600,000. Close your parentheses. Divide by x. Okay. So when I go to my table, values I get are 1,100 with the 1,000. 10,000 is going to be 560. And 100,000 is going to be 506. Okay. D. What is the horizontal asymptote for the graph of the average cost function? C with line above it. Describe what it represents for the company. So really, this is going to be the exact same. Obviously, it's the horizontal asymptote. It's going to be the 500x over x is 500. So y equals 500. Again, that's that lowest cost. So again, the more you produce, the closer you're going to get to it. Now we put one more thing in this. So last example, then we're done. So if an object moves at an average velocity v, the distance s is covered in time t is given by the equation s equals vt. So s's position equals velocity times time. Objects using this formula to move in a uniform motion. Our objects use this formula to move in a uniform motion. Then the formula for time is t equals s over v. So if we were looking for time, all we did was just divide the v over. So 2 commuters drove to work a distance of 40 miles and then returned again on the same route. The average velocity on the return trip was 30 miles per hour faster than the average velocity on the outgoing trip. Express the total time required to complete the round trip t as a function of average velocity of the outgoing trip x. So we're going to use, time equals s over v, so position over velocity. So if we're dealing with time, so t of x is going to be our function. So we want the total time for the round trip. So on the way there, we covered our 40 miles. And we went a certain speed. And then we're adding to it on the way home. We still went that 40 miles. But we went that speed plus we went 30 miles per hour faster. So plus 30 velocity faster. And that's going to be as far as we could take this. We're going to need more information from here. And I should say velocity then is x instead of v. Because we don't know what our velocity is. This way, whatever our velocity we put in there, boom, we're going to get it. And we'd have what our time took. And that's it. That's this lesson. So, I know it's a little bit of a longer lesson. Again, if there's things that you need to go back and rewatch, or you want to pause to write stuff down, or even just to pause and just kind of figure out, okay, what is he all talking about there? Please do so. If you have questions, please let me know as well. Otherwise, until next time, we'll talk to you later, guys.